The gas coming from 3I Atlas doesn't match any known comet, warns Professor Brian Cox. NASA and the European Space Agency have seen comets erupt water, carbon dioxide and carbon monoxide for decades, but the third interstellar object ever found just broke the rules. Its spectrum screams with 8 times more carbon dioxide than water, barely any carbon monoxide, and a flash of pure nickel vapor, something no solar system comet has ever shown. Not even Oumuamua or Borisov looked like this. Astronomers are stunned. If this isn't comet chemistry, what else could survive a journey across the stars? Everything we thought we knew about cosmic visitors is now under threat, and what we'll uncover next could force us to rewrite the story of our own solar system. Comets are often called dirty snowballs, but their true recipe is more precise. At their core, most comets are chunks of ancient ice and dust, leftovers from the birth of the solar system. When these icy bodies approach the sun, sunlight begins to work its magic. The surface heats up and frozen gases trapped for billions of years start to vaporize. This process, called outgassing, creates the spectacular coma and tail that define a comet's appearance. For decades, NASA and the European Space Agency have used spectroscopy to decode what's in that glowing cloud. Imagine shining a beam of light through fog. Each molecule leaves a telltale mark, a set of lines in the spectrum. The brightest of these by far comes from water vapor. In nearly every comet studied, water dominates the coma. Carbon dioxide and carbon monoxide are present too, but always in smaller amounts. Surveys of hundreds of solar system comets reveal a familiar pattern. Water vapor is usually the main ingredient, making up the bulk of the gases released. Carbon dioxide appears next, but rarely exceeds a third of the water's abundance. In fact, the typical carbon dioxide to water ratio falls between 0.05 and 0.3, meaning water outnumbers carbon dioxide by at least 3:1. Carbon monoxide is even less common, sometimes matching carbon dioxide, sometimes barely detectable at all. The Rosetta mission to Comet 67P made this chemistry clear. Instruments on board watched as water vapor poured off the nucleus, with carbon dioxide and carbon monoxide following behind. Other famous comets, Hale-Bopp Hyakutake, even the interstellar visitor Borisov, fit the same mold. Each time the numbers stack up, water first, carbon dioxide second, carbon monoxide a distant third. This chemical fingerprint isn't just a curiosity. It sets the baseline for what astronomers expect from a comet. Whether it's from the Oort cloud, the Kuiper belt, or even drifting in from another star, deviations happen. A few comets are rich in carbon monoxide. Others might show a spike in ammonia or methane. But the core pattern holds. Water leads the dance, carbon dioxide and carbon monoxide play supporting roles. That's the rulebook every comet so far has followed. James Webb's first spectra of 3I Atlas stunned the astronomy world. Instead of the usual dominance of water vapor, the data showed a chemical fingerprint that defies every known pattern. The carbon dioxide emission band at 4.3 microns blazed across the readings, overwhelming the faint signature of water. For every molecule of H2O, there were about 30 molecules of carbon dioxide. No solar system comet, not even the wildest outliers, comes close. Most barely reach a third as much carbon dioxide as water. Here, water is a footnote. Carbon dioxide calls the shots. Carbon monoxide, the other usual suspect, barely registers. The ratio of carbon monoxide to carbon dioxide hovers around 0.2, far below what's expected for an object this active. Multiple observatories confirmed the result. Spherex, VLT, ALMA and Keke all measured the same shocking numbers. The carbon dioxide is not just abundant, it's tightly packed near the nucleus, forming a dense inner coma. H2O, by contrast, is faint and scattered, almost lost in the noise. Then comes the metallic twist. High-resolution spectra from the Very Large Telescope revealed bright lines from atomic nickel streaming off the coma. But the usual companion ion is missing. Not a single feline rises above the detection threshold. In every solar system comet ever studied, nickel and iron vaporize together in proportions matching meteorites and the sun. Here, only nickel escapes. The nickel-to-iron ratio soars more than 10 times higher than any previous comet, breaking the rules of both chemistry and cosmic formation. Lab teams rushed to test for errors, pipeline calibrations, background subtractions, instrument cross-checks, all confirmed the anomaly. No artifact, no glitch, just a real physical signature that refuses to fit any model. The gas pouring from 3I Atlas is not just rare, it's unique. The rules that have governed comet science for decades fall apart in the face of this data. If this is what interstellar chemistry looks like, the universe is stranger than anyone imagined. Orbital prediction is supposed to be a solved problem. Plug in the mass, the velocity, the sun's gravity, and a comet's path should trace out with pinpoint precision. For decades, this model has worked, whether for icy wanderers from the Oort cloud or interstellar visitors like Borisov. But with 3I Atlas, the numbers refuse to cooperate. As soon as the discovery data hit the minor planet center, dynamicists worldwide raced to fit its orbit. Early solutions agreed this was a hyperbolic intruder, inbound at more than 50 km/s, with an eccentricity over 6. Observatories stacked hundreds of position measurements, each with its own timestamp and error bar. In theory, these should line up predicted versus observed, dot for dot. Instead, the residuals, the tiny differences between where 3I Atlas was supposed to be and where it actually appeared, began to drift. Not wildly, not enough to trigger alarm in the first week, but enough that the overlay never quite snapped into focus. The mean deviation per observation hovered around half an arcsecond, translating to several hundred kilometers at the object's distance. For a nucleus likely between 3 and 5 kilometers wide, that's more than just measurement noise. The first suspects were the usual ones, outgassing jets. When sunlight hits a comet, pockets of volatile gas burst from the surface, acting like miniature thrusters. The effect is real. Rosetta's mission to 67P showed that just 10% of the surface could spin the entire nucleus, shifting its path by measurable amounts. For 3I Atlas, though, the math doesn't add up. The CO2 jets pouring from its surface are powerful, but even at 30 times the water vapor, their total momentum falls short. Analysts ran the numbers again and again, plugging in every plausible outgassing scenario. No combination could nudge an object this massive by the observed amount. Each new observation only deepened the puzzle. The drift persisted, sometimes growing, sometimes shrinking, but never vanishing. No standard jet model could close the gap. The rulebook, gravity plus outgassing, suddenly looked incomplete. For the first time since interstellar objects entered the solar system, astronomers faced a mechanical inconsistency they couldn't explain away. The mystery was no longer just chemical. Now physics itself was on trial. 6 years before 3I Atlas, astronomers caught their first real glimpse of an interstellar visitor. In October 2017, telescopes locked onto an object later named Oumuamua. At first, it looked like a cosmic oddball. No coma, no tail, just a tumbling shard of rock or ice. But as it sped away from the sun, something stranger happened. Its path began to drift, veering ever so slightly from the line gravity alone would dictate. The deviation was small but real, confirmed by dozens of observatories and published in peer-reviewed journals. The usual explanation for a comet's course correction is outgassing, jets of vapor acting like miniature thrusters. Yet Oumuamua showed no sign of gas, no halo, nothing to suggest it was venting anything at all. The debate erupted almost overnight. Some researchers argued for invisible hydrogen ices, others for exotic physics. Avi Loeb, a Harvard astrophysicist, went further, asking whether we might be looking at engineered propulsion, a solar sail perhaps, or a fragment of alien technology. Most of the field pushed back, but the question hung in the air. What kind of object moves without leaving a trace? Then came 2I Borisov in 2019, the second interstellar object ever confirmed. Borisov was different from the start. Its spectrum matched the familiar profile of solar system comets: water vapor, cyanogen, carbon monoxide. Its coma and tail followed the rulebook, and its trajectory fit gravitational models without a hitch. Borisov reassured astronomers that not every visitor from beyond would break the mold. If anything, it looked like a standard comet, just one that happened to be born around another star. Now, with 3I Atlas, the pattern grows more tangled. One object, Oumuamua, defied gravity without a trace of gas. The next, Borisov, played by the rules, and now Atlas, bigger and brighter than both, brings a new kind of puzzle. A chemical fingerprint that doesn't match any known comet, and a trajectory that refuses to be explained by the usual physics. 3 visitors, 3 different stories. If there's a common thread, It's that each arrival deepens the mystery, pushing astronomers to widen their search for answers. What else might be out there, waiting to rewrite what we think we know about the universe? The search for answers begins with the most conservative models. Some researchers argue that 3I Atlas is showing us chemistry from a planetary system unlike anything in our backyard, a world where carbon dioxide dominates and water ice is scarce. Exotic ices forged in the coldest reaches of a distant protoplanetary disk could have survived ejection and interstellar travel.